Hi, Stu Schwartz from MasterMathMentor.com. This is video BC06. The topic is Euler's method. It covers the BC manuals, pages 31 and 32. In the United States' first orbital flight around the Earth in 1962 with astronaut John Glenn, the astronauts at NASA had a very difficult problem. The capsule was orbiting in an elliptical orbit about the Earth. At a certain point in time, they needed to fire the retro rockets so that gravity would take over and turn the path into a parabolic one. Timing had to be split second. Burn too soon, and the capsule would burn up due to air friction as it entered the atmosphere. Burn too late, and the capsule would skip across the atmosphere into space. This exact moment was called the go, no-go moment. There are so many variables in these types of equations, and they turned out to be very difficult to approximate to the specifications both the military and astronauts demanded. One small error in the calculations for when to slow the spacecraft down to start its descent into the atmosphere could result in it burning up, and the Navy demanded that NASA be able to bring the capsule down within a 20 square mile of ocean. Katherine Johnson, as portrayed in the popular movie Hidden Figures, was integral to figuring out how to solve this problem, and in doing so exposes one of the reasons math is both really important and really cool. At that time, there was no known differentiable formula that changed an elliptical equation into a parabolic one. Without this knowledge, NASA couldn't launch because there would be no way to bring Glenn home. In the movie, she has a eureka moment while staring at a blackboard and realizes it's not new math that was needed, but old math that might be the solution. She turns to Euler's method, which in layman's terms allows the mathematician to approximate a differential equation numerically without actually ever really solving it. In this video, we learn how to perform Euler's method and solve the same types of problems on which Katherine Johnson labored. Leonhard Euler, and yes, that is the correct pronunciation, was an 18th century Swiss mathematician, physicist, astronomer, geographer, logician, and engineer who made important and influential discoveries in many branches of mathematics, including calculus. Euler introduced and popularized several notational conventions through his numerous and widely circulated textbooks. Most notably, he introduced the concept of a function and was the first to write f of x to denote the function f. He also introduced the modern notation for the trig functions. He was the first to use the letter e for the base of the natural log, that is now known as Euler's number. He used the Greek letter sigma for summations and the letter I to denote the imaginary unit. The use of the Greek letter pi to denote the ratio of a circle's circumference to its diameter was also popularized by Euler. Euler was a giant in mathematics. Back at the tail end of AB calculus, you learned a technique to solve separable differential equations. A DEQ that was separable meant that we can get all the x's on one side and all the y's on the other. Let's see how we went about solving a problem like that. Suppose we have dy dx equals xy squared. First step is to divide both sides by y squared, and we get dy over y squared equals x dx. We have separated the equation. We now integrate both sides. The integral of dy over y squared is equal to the integral of x dx. And when we integrate, we get negative 1 over y equals x squared over 2 plus c. We will then multiply the entire equation by 2y, and we get negative 2 is equal to x squared y plus cy, as 2 times c is simply another constant. And our final answer is y equals negative 2 over x squared plus c. However, there are many differential equations that are not separable. No matter how much you try, no matter what you do, there is no way to get all the x's on one side and all the y's on the other. For instance, dy dx equals x plus y, or dy dx plus y equals e to the x. Dy dx equals quantity x squared plus x times the quantity y squared plus y plus 1. Or x dy dx plus y dy dx equals x. In college, a number of you will take a course on solving differential equations. It is a branch of calculus that has an entire course devoted to it. Towards the end of this manual, you will find a section to solve first-order differential equations that are not separable. So for now, we will examine Euler's method. Euler's method is a numerical technique to approximate the solution to a differential equation. It is similar to what we did when we learned Riemann sums, when we took a number of rectangles to find the area under a curve, and we found that the more rectangles we used, the closer our answer approximated the definite integral. The same type of thing happens with Euler's method. In Euler's method, we start at a certain point on the curve, and we draw a tangent line at a length of delta x. We then look down on the curve, find its slope, and draw another tangent line. We then look down on the curve, find its slope, and then draw another tangent line. And we can continue to repeat this process. As you see, our unknown solution to the DEQ is being created by the lines and the arrows. It is getting further from the actual curve. That is the algorithm for Euler's method. A better description is shown with this graphic. We are given a differential equation whose unknown solution is the exact function y equals f of t, shown in blue. By using Euler's method, we approximate the solution with tangent lines. At first, the solution from A0 to A1 is very close. But as you can see, as we move from A1 to A2, A2 to A3, A3 to A4, the solution, which is called the Euler approximation, is getting worse. However, if our distances between our values T0, T1, T2 are small, the Euler approximation will be very, very good. Euler's method is an iterative process. We will start and go through this process, coming up with a new value that we will use the next time we go through the process. The value keeps updating, and we will stop when we reach the desired result. Rather than explain the process, we will look at a problem at the same time and work the problem using Euler's method. So we have problem 1 that states if f of 0 equals 3, approximate f of 2 using 4 steps if dy dx is equal to x plus y. To perform Euler's method, I recommend a table with 4 columns: x, y, dy dx, and dy. We start by stating that our original point is 0, 3 because f of 0 is equal to 3. We then calculate the slope dy dx at the point xy using the differential equation. Since dy dx is equal to x plus y, dy dx equals 0 plus 3, which is 3. Since f of 0 is given, and we want f of 2, and we will be using 4 steps, then our delta x is simply 2 divided by 4, which is 1/2. So we will now use the formula that dy is equal to dy dx times delta x. This represents the approximate change in y along the graph. So when dy dx is equal to 3, delta x is equal to 1/2. That makes dy equal to 1.5. We are now ready for the second line. Our new value of x is the old value of x plus delta x. So 0 plus 0.5 is 0.5. Our new value of y is equal to the old value of y plus dy. So 3 plus 1.5 is 4.5. And we're now ready to start the process again. Dy dx is equal to x plus y, which is 0.5 plus 4.5, which is 5. Therefore, dy is equal to dy dx times delta x. 5 times 0.5 is 2.5. We are now ready for the third row. Our new x equals our old x plus 0.5. 0.5 plus 0.5 is 1. Our new y is equal to our old y plus dy. 4.5 plus 2.5 is 7. We now start the process again. Dy dx is equal to x plus y, which is 1 plus 7, which is 8. And therefore, dy is equal to dy dx times delta x. 8 times 0.5 is 4. The fourth row. Our new x is 1 plus 0.5, which is 1.5. Our new y is 7 plus 4, which is 11. Therefore, dy dx is 1.5 plus 11, which is 12.5. And dy is equal to 12.5 times 0.5, which is 6.25. Finally, the last row. Our new x is 1.5 plus 0.5, which is 2. And our new y is 11 plus 6.25, which is 17.25. We stop here because this is our answer. We wanted an approximation for f of 2, and it is 17.25. Number 2 reads, if f of 0 equals 4, approximate f of 1 using 4 steps if dy dx is equal to x plus 4 over y. This problem can be solved as a separable differential equation. You would get y dy is equal to quantity x plus 4 dx, and we could actually solve it by integration. But let's do the problem by Euler's method. When constructing your table, I suggest putting in all the x values first. You're starting at f of 0, and you want to end up at f of 1. So 1 minus 0 divided by the 4 steps makes your delta x 0.25. Our first y is 4, and therefore dy dx is 0 plus 4 over 4, which is 1. Dy, therefore, is 1 times 0.25, which is 0.25. So our new y is 4.25. Our dy dx is 0.25 plus 4, which is 4.25 divided by 4.25. And we get 1 again, making dy 0.25 again. Our next value of y is therefore 4.25 plus 0.25, which is 4.5. So our new dy dx is 0.5 plus 4 divided by 4.5, which is 1. And we're starting to establish a pattern here. And notice that all the dy dx's are 1, all the dy's are 0.25, and therefore our final value for y will be at the 0.15. Problem number 3 is an involved problem that we will do in stages. Let T of t denote the room temperature in Fahrenheit of a cup of coffee at time t, measured in minutes. Room temperature is 70 degrees, and the coffee is 190 degrees when it first comes out of the microwave. The coffee's temperature is described by the differential equation dt dt is equal to negative 0.1 times the quantity t minus 70. The first thing we will do is to complete the table using Euler's method for 10 minutes. In completing the table, t runs from 0 to 10, where delta t is equal to 1. This makes completion of the table very easy. Our first point is 0, 190, and by the formula, dt dt is equal to negative 12. And that makes d capital T equal to negative 12 times 1, which is still negative 12. This will happen all the time. We'll be multiplying by 1. So our new value of t is equal to 178. Our next value of dt dt is equal to negative 10.8. And therefore, to get the next value of capital T, we simply add negative 10.8 to the 178. So as we complete the chart, we will simply be adding the values of dt dt down to onto the current values of t. And we get all the points shown in red. We are given a slope field, and now we plot the points, connecting them with straight lines. And we see that the points do a very good job of following the slope field. The differential equation given is separable, which means that we can solve it. So we have dt over t minus 70 is equal to negative 0.1 dt. We can integrate those expressions and get the natural log of the absolute value of t minus 70 equals negative 0.1 t plus c. And therefore, t minus 70 is equal to ce to the negative 0.1 t. We now use the fact that at time equals 0, capital T temperature is equal to 190. So we get 190 minus 70 is equal to C, which is equal to 120. So our final equation is temperature is equal to 70 plus 120 e to the negative 0.1 t measured in minutes. So using this formula, we calculate the actual temperature of the coffee at t equals 0, t equals 1, as shown in blue in the table. Finally, we plot the actual values in blue onto the slope field. Notice how the red points, which are the Euler's method's approximations, are getting slightly further away from the blue points as time gets larger. This always happens with Euler's method. Still, Euler's method is a very good way of approximating the temperature at T is equal to 10. 4 reads, to determine the approximate location of the relative minimum for the function whose differential equation is given by dy dx equals 2x minus y plus 2, Euler's method with step 0.25 is used. If the initial value is the 0.04, on what interval does the relative minimum for y equal f of x lie? If you recall, in AB calculus, we did relative minimum problems a lot. Our usual technique was to find the derivative and find when the derivative switches from negative to positive, or the function switches from decreasing to increasing. Unfortunately, we cannot solve for y. So we will try to get an approximate value for y using Euler's method. We set up our table with 4 columns, x, y, dy, dx, and dy. Our x's start at 0, and since our step is 0.25, they go up 1/4, 1/2, 3/4. Our initial point is 0, 4. From the equation for dy dx, we get dy dx equals -2, and dy is equal to -1/2. Euler's method problems tend to get quite messy. In this problem, I'm going to work with fractions until I'm forced to switch to decimals. The second row gives our value of x, which is 1/4, our new value of y, which is 4 minus 1/2 or 7/2, and by our formula dy dx is equal to -1, and dy is -1/4. The next row, we have x is 1/2, our new value of y is 13/4, and dy dx by our formula is -1/4. That gives a dy to be -1/16. We then go down to 3/4 for x. Y is 51/16, and dy dx is now 5/16. And we can stop because we notice that dy dx has switched from negative to positive, which means that this must happen somewhere between x is equal to 1/2 and x is equal to 3/4. 5 is a type of problem that comes up many times. You are given a differential equation which you can solve, and therefore find the value of the function at some particular value. You can also approximate the solution using Euler's method, and you are trying to find the difference between the exact value and the Euler approximation at that specific value. So this problem reads, consider the differential equation dy dx equals e to the 1 minus y with initial condition f of 0 equals 1. Find the difference between the exact value of f of 1 and the Euler approximation of f of 1 using 2 equal steps. We will start with Euler's method. Our x values are 0, 0.5, and 1. Our initial point is 0, 1, and therefore by our formula dy dx is equal to 1. And since delta x is 0.5, our dy is 1 times 0.5, which is 0.5. That makes our next value of y 1 plus 0.5, which is 1.5. We now plug in that 1.5 into e to the 1 minus y, and we get e to the -0.5, or 1 over the square root of e. Therefore, dy is 1/2 of that, or 1 over 2 square root of e. So our final value for y is 1.5 plus 1 over 2 square root of e. Thankfully, we don't have to go any further into the table. So let's now solve the differential equation. We get dy over e to the 1 minus y is equal to dx. And we can write 1 over e to the 1 minus y as e to the y minus 1. So we have the integral of e to the y minus 1 dy is equal to the integral of dx. And that gives us e to the y minus 1 is equal to x plus c. Plugging in the point 0, 1, we get 1 equals 0 plus c, and that gives us c equal to 1. So our equation is e to the y minus 1 is equal to x plus 1. We need to solve this for y, so we write this problem as y minus 1 is equal to the natural log of x plus 1. Or y is equal to 1 plus the natural log of x plus 1. And y of 1 is 1 plus the natural log of 2. So finally, the difference is the absolute value of 1.5 plus 1 over 2 square root of e minus quantity 1 plus natural log of 2. I used an absolute value sign here because I'm not sure which number was bigger. However, this turns out to be 0.5 plus 1 over 2 square root of e minus the natural log of 2. On the AP exam, you usually do not have to take Euler's method out to too many steps because it can get very messy. There are applications on the internet that will solve problems with Euler's method where you input the function and you put in the initial point and the delta x, and it will come up with all the intermediate values. All you need to do is Google Euler's method.